All right, let's get right into it. Today, we're talking about a truly fascinating piece of engineering, something that happens miles beneath our feet. It's a high-pressure, high-stakes mission to unlock massive amounts of trapped energy. So here's the question, right? Once all the easy-to-get oil has been pumped out of a well, there's still a ton of it left behind. So what's the trick? How do you wring out the last few drops from a sponge that's made of solid rock deep inside the earth? And this isn't some small problem. The scale is just mind-boggling. We are literally talking about a billion-barrel problem. You can think of these old oil fields as giant vaults packed with energy, but the key is missing, and all that treasure is locked tight. And here's why it's so tricky. The rock down there isn't some big, open, underground lake of oil. Nope. It's much more like a sponge. And once you've squeezed it once, a whole lot of oil is still stuck in there, just clinging to the inside of millions of tiny little pores. You can't just pump harder. You gotta get clever. So what's the secret key to this vault? Well, you might be surprised. It's something we hear about all the time. Carbon dioxide, CO2. But hold on, this isn't the CO2 you're thinking of. To pull this mission off, it has to be turned into something else, something special. And that special state is called a supercritical fluid. Now, this stuff is straight out of science fiction. If you crank up the pressure and the heat on CO2 past a certain point, it just stops being a gas and it stops being a liquid. It becomes this incredible hybrid that has the properties of both. And this is where you see why that matters so much. Regular CO2 gas, it just kind of sneaks past the oil. It's too weak to do anything. But that supercritical CO2, wow. It has the density of a liquid, so it has the muscle to push the oil, but it flows as easily as a gas, so it can get into all those tiny little nooks and crannies. It's the perfect tool for the job. The fancy engineering term for this is miscible displacement. But forget the jargon for a second. Just think about stirring honey into hot tea. That thick, sticky honey becomes thin and runny, right? That is exactly what the supercritical CO2 does to the trapped oil. It mixes with it, makes it flow, and makes it way easier to push out of the rock. Okay, so after all that crazy science and engineering, is it actually worth it? Oh yeah, we're talking about getting another 10, even 20% more oil out of a well that was pretty much considered done. For a huge oil field, that's not just a little extra, that's millions and millions of barrels. A massive payoff. But you don't just show up with a pump and hope for the best. No way. Success here is all about the plan. This is a full-blown engineering mission, and almost all the critical work happens in simulations and on paper long before a single piece of equipment even gets to the site. And that pre-job checklist is intense. First, you've got to know your battlefield, right? So they analyze everything about the well, the temperature, the pressure, what the rock is like. All that data tells them exactly what state the CO2 needs to be in. Then it's all about the numbers, calculating the precise pressures to stay safe. And finally, they map out the whole game plan, second by second. Okay, the planning phase is over. The blueprint is locked in. Now, it's showtime. This is where the big iron rolls in and things get really, really interesting. And the gear they use for this is on another level. I mean, we're talking about pumps so powerful they can literally make the ground vibrate. All this heavy-duty, articulated steel piping all connected together. And then you have the brains of the operation, a whole network of sensors and valves keeping track of every little thing in real time. And the pressures involved here, get ready for this, 15,000 psi. To put that in perspective, your car tire is maybe 35 psi. This is just astronomical. Simply containing that kind of force without anything breaking is, frankly, an engineering miracle. And actually doing the injection isn't as simple as flipping a switch. It's all about control. They start by gently filling up the lines because you don't want to shock the system. Then they start pumping, but super slow at first, just to let everything stabilize. And only then do they slowly, carefully ramp up to full speed, with eyes glued to the data, ready to make tiny adjustments at a moment's notice. But let's be real, when you're dealing with these kinds of pressures and all this wild chemistry, a lot can go wrong. I mean, really wrong. So how do these engineers handle the risks and navigate this danger zone? Okay, risk number one is ice plugs, but we are not talking about your average icicle here. This stuff is called a hydrate. It happens when high-pressure CO2 hits just a tiny bit of water at low temperatures, and it basically forms concrete inside your pipes. It can stop the whole job dead in its tracks and create a very dangerous situation. So how do you fight these things? With a few different tricks. You can pump in methanol, which is pretty much industrial-strength antifreeze. You can use special heaters to keep the lines warm. But the best defense? Just keep that CO2 in its happy place, that supercritical state where hydrates just don't like to form. The next big bad guy is invisible, but just as nasty: corrosion. See, when CO2 and water get together, they create something called carbonic acid. Yep, it's the same stuff that makes your soda fizzy, but at these incredible pressures and concentrations, it's not so harmless. It can literally eat right through solid steel. So the game plan here is twofold: armor and prevention. They use special chemicals that actually coat the inside of the pipes to protect them. The equipment itself is built from super tough, certified, corrosion-resistant steel. And, the easiest way to avoid the problem is to do everything possible to keep water out of the system in the first place. And the last major risk, well, it's just pure physics, brute force. If you suddenly stop or change the flow at these extreme pressures, you create a massive shockwave. Engineers call it a CO2 hammer, and it's exactly what it sounds like. It's a force that can violently shake, bend, or even rupture the equipment. And the only way to defend against that is with control and finesse. That's why that slow, gradual startup is so critical. The pumps also have these built-in shock absorbers, but really it comes down to a skilled operator with their hands on the controls, constantly watching the data and making tiny adjustments to keep everything running perfectly smooth. So when you step back and look at the whole picture, you see this really elegant pattern, right? For every single major challenge, the trapped oil, the insane pressures, the technical risks, there is a specific, sophisticated, and brilliant engineering solution that leads to a safe, controlled, and successful result. It's a masterclass in high-stakes problem solving. So, this is so much more than just pumping gas down a hole. It's a high-tech, high-pressure, precision-guided mission. The best way to think about it is like a kind of industrial surgery, giving the Earth a very, very carefully planned